Okay, Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So now we will start with our second part of chapter number 1, which is about the basic equation that we will use in the subject of turbomachinery. And the basic equation for this topic actually is a Euler equation. Okay, now about the basic principle law that we will use in this turbomachinery subject. So there are a few basic physical law that we will use, and if you refer to basic physical law, there are two groups of equations or physical law that we will implement for this turbomachinery. First, under the fluid mechanic, so we have the equation of in terms of the continuity equation of flow, the momentum equation, and the equation or the physical laws under the thermodynamic are first law of thermodynamic, the steady flow energy equation, and also the second law of thermodynamic. So all these equation from fluid mechanics and also thermodynamic will use to helps or to aid us to get or to derive the equation for the efficiency of a turbomachinery, such as the compressor and also the turbine. So for the equation that I mentioned before, which is the Euler equation that we will use throughout the subject, actually is come from or derived from the momentum equation. Okay, so from the momentum equation, we'll get the Euler equation for pump, for the compressor, and also for the turbine. Okay, now about the Euler's equation for the compressor and also for the turbine. So before we derive the equation for this compressor and also turbine, it is important to look at the physical condition of a turbomachinery. Okay, so this figure actually is a turbo machine that we call a radial flow compressor. Okay, so if I ask you what is the actual name for this component, can you give me the actual name for this component? So I give you 5 seconds to think about it. So you get the answer. So this device actually is a turbocharger, which is consists of a radial flow compressor and also radial flow turbine. So you can see in the figures. But now we just want to concentrate about what I call second part of the turbocharger that we refer as the radial flow compressor. Okay, so we have entry section for the compressor, and also the exit section for the compressor. So in terms of flow direction, so the flow or the fluid will enter the entry section, and due to the shape of the radial flow compressor blade, so we get what we call the radial flow of fluid throughout the compressor. Okay. Okay, so now let we take out the rotor of the compressor. So you will get the second photo as shown in the slide. Okay, and this part we call rotor or compressor rotor. Similarly, for this rotor, we try to identify where is the location of the entry section and also exit section. So we have entry section, show the figure, and also exit section, and flow direction in axial direction at the beginning, where the pink dot represent the fluid particle, and then this fluid particle will flow through the compressor rotor, and the direction is depend on the shape of the rotor blade. So this particle will come out from the rotor section and exit from the rotor. So these are the basic physical principle before we derive the Euler equation for the compressor and also for the turbine. Okay, so this schematic diagram actually is a control volume for a generalized turbo machine, which is referred to the simplified schematic diagram for the rotor that we already discussed in previous slide. Okay, so in this simplified schematic diagram, you can see that the parameter or the variable that involved for the compressor rotor. So what we have here, we have the torque or the moment tau, which is equal to the moment of the external force acting on fluid rotate around the axis of A. So we have omega, which is represent the angular velocity, radius, the radius of the circle at the inlet and also at the outlet, tangential velocity, which is referred to the velocity of the fluid at the inlet and also at the outlet. So number 1 represent the entry condition, and also number 2 represent the exit condition. So now let we compare between this schematic diagram with the actual compressor rotor. So now we want to try to relate the parameter that involved in schematic diagram with the actual rotor. So we will have AA axis of the rotor, the moment of the external source tau A, and the angular velocity of the rotor omega, first circle at the inlet with radius R1, second circle with radius R2 for the outlet of the rotor. So pink dot represent the fluid particle at the inlet, and this particle will flow through the rotor, depend on the blade, the direction depend on the blade shape, and this particle will come out from the rotor at the outlet of the rotor. So, and this will give the direction, the actual direction or the absolute direction of the fluid. Okay, tangential velocity actually is the velocity of the particle at the inlet of the rotor, c theta 1, and also we have c theta 2, the tangential velocity of the particle at the outlet of the rotor. Okay, so these are the parameters or the variables that involve for the compressor and also turbine before we derive the equation for the Euler equation. So based on the momentum equation, so we'll get the rate of which the rotor does work on the fluid, which is referred to the compressor, where tau omega equal to mass flow rate multiplied with the component of velocity difference, which is consists of blade speed u, which is equal to omega multiplied by r, radius of the rotor at the inlet and also at the outlet. Okay, so from this equation, if we divide this equation with mass flow rate, so we will get the Euler equation. For example, the Euler's equation for the compressor. So we will get the work done by the rotor on the fluid per unit mass, or we call specific work. So we get delta WC represent the compressor equal to WC dot divided by mass flow rate m dot, which is equal to tau A times omega divided by mass flow rate equal to blade speed multiply by tangential velocity at the outlet minus blade speed multiply by tangential velocity at the inlet. So this is the equation of Euler equation for the compressor, and the value must be greater than 0. However, for the turbine, by referring to the same equation and divide by mass flow rate, so you will get the work done by fluid on the rotor per unit mass or specific work for the turbine. Delta WT, T stand for the turbine, equal to WT dot divided by M dot, equal to tau times omega divided by M dot, equal to velocity component different, U1 times C theta 1 minus U2 times C theta 2. So the value must be greater than 0. So we have similar equation if you compare to compressor and also the turbine. Okay. Okay, now in order to test your understanding on this topic, please answer this question. So by referring to the general Euler's equation, guess the Euler's equation for axial flow turbine or axial flow compressor with constant radius as shown in the figure. Give your reason. So you have to answer the question through my blog, where you have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. Clue is given in the link. Okay, good luck. Okay, end of part number 2. Assalamualaikum.